Welcome to the CESTiCC webinar series. Our presenter today is Dr. Fujian Tang of the School of Civil Engineering, Dalian University of Technology, China. He will be presenting on Chloride Induced Rebar Corrosion in Concrete, Mechanism, Prevention, Monitoring, and Assessment. This presentation is eligible for professional development hour credit. So if you are interested in getting a certificate for professional development credit, please send me an email after the webinar. So a recording of this will also be made available on the CESTiCC website within a few days. And with that, I'd like to hand it over to Dr. Tang.
Okay, thank you for introduction. Before the lecture, I want to thank Professor Shi to invite me to give this lecture. And the title of this lecture is Chloride Induced Rebar Corrosion in Concrete, Mechanism, Prevention, Monitoring, and Assessment. This is the outline of the lecture. I will start with a background and introduction, talking about the corrosion cost and the corrosion related safety issue, and come up with 4 questions about the corrosion. So the second part is enamel coating. Actually, it's a primary research when I was a PhD student at Missouri University of Science Technology from 2008 to 2013. And part 3 is optical fiber corrosion sensor. So it's my research when I was a postdoctor at Missouri University of Science Technology from 2014 to 2016. And the first part is assessment method for corrosion reinforced concrete structure. And last one is acknowledgement. So this background introduction, corrosion is not only an economic burden to the US economy, but also a safety issue. So according to a report released by NACE International in 2002, we can see here the corrosion cost for highway bridges around $8 billion. And the indirect cost due to the delay of traffic and the loss of productivity is estimated to be 10 times greater than the direct cost. And also corrosion is a safety issue. So in 2007, a state of Minnesota, this bridge collapsed, killing 13 people, injuring 145. Although corrosion is not the primary cause of this bridge failure, it has been found on some critical structural elements. After 3 years, the city closed another bridge. That's because some corrosion found on several cables in the pre-stressed girders. So now for questions. Question 1, how does corrosion affect structures? Question 2, what method can be taken to prevent corrosion? Question 3, how to monitor steel corrosion in concrete? And question 4, how to assess structure performance after corrosion? So this is question 4. How does corrosion affect structure performance? As we know, corrosion is an electrochemical process. The iron reacts with oxygen in the presence of water to produce some corrosion products. The volume of the corrosion product is usually 2 or 6 times greater than the steel it consumes. So this expansive volume would generate some tensile stress in the concrete. When the tensile stress of concrete reaches a tensile strength of concrete, so concrete crack. And the corrosion also reduces the cross-sectional area of steel bar and some mechanical property degradation. And also corrosion damages the interface between the steel and the concrete, so reducing the bonding strength. So now question 2. So what measures can be taken to prevent corrosion? Over the past years, a lot of measures have been developed to prevent corrosion, which can be divided into 2 categories. First is to improve concrete core property. Second, to modify reinforcement steel. As for the concrete core properties, we can first we can use some particle coating directly on the surface of concrete, or we can use small water similar ratio and optimize aggregate gradation, or add some high performance admixture like fly ash silicate film, slags, or some corrosion inhibitors. And also, as for the steel bar, we can use coated steel bars. We can also use stainless steel, but the stainless steel is very expensive, not economic. And some FRP bar can also be used, but structures reinforced with FRP bars brittle is not safe. And the last one is we call it cathodic protection. And amongst all these methods, use of particle coating is considered to be the most economic and effective ways to protect steel bar from corrosion. Two of the most widely used coatings are epoxy coating and zinc coating, but neither of them is perfect. For epoxy coating, the coating can be easily damaged during transportation and handling, and the epoxy coating has a weak bond with the steel bar and the surrounding concrete. As for the zinc coating, we know the pH value of the concrete is around 13, so it's an alkaline environment. The zinc will react in an alkaline environment to produce some hydrogen gas. So this hydrogen gas would increase the porosity at the interface between the steel and the concrete, so reducing the bond strength. So any other coatings? Yes. The enamel coating. Actually, enamel coating is an inorganic coating. It's a material made by fusing powdered glass to a metal substrate by firing usually between 750 to 850 degrees C. So it's widely used for household purpose like industrial container and construction industrial. So this is a cooking utensil. The middle one is like as a chemical container. Third one is like for the construction, some building decoration. So enamel coating has some advantages. First is chemically adhere with substitute steel. So it's a chemical bond with the steel. Second, it can enhance the bond strength with surrounding concrete. Third, as a barrier layer, it can prevent penetration of chlorides. Fourth, its property is flexible. It can be modified by adding different oxides. Last is it has very stable physical and chemical properties. The only disadvantage is brittleness. It's very brittle, so it may crack during bending or tension. But this could be minimized in application precast construction. So enamel coating could be a good option to protect steel bar from corrosion. And that's one concern. The concern is that the enamel coating is very smooth, and so the bond strength is not too high. So during my PhD study, we proposed we modified the commercial available enamel coating by adding calcium silicate and sand particle to improve the bond strength. Why calcium silicate? Because this calcium silicate could react with concrete, so resulting in chemical bond with the concrete. As for the sand particle, it can increase the surface roughness of enamel coating, so increase the mechanical interlocking and the bond strength with concrete. So let's take a look at the corrosion performance of this cement, calcium silicate modified enamel coating. So actually, we tested two coatings. The first, mixed enamel coating. The mixed enamel actually is 50% pure enamel with 50% cement. Pure enamel is a commercially available product from PEMCO International. And also there's a double enamel coating. Double enamel coating consists of two layers, pure enamel as inner layer and mixed enamel as outer layer. So table 1 just shows a typical chemical composition of pure enamel. We can see the primary chemicals is silicate dioxide, is 44%. And also it consists of the conium dioxide, nickel oxides. So this coating has a very high alkaline resistance and adherence strength with substitute steel. So as for the cements, because the primary chemicals for cement is silicate dioxide and calcium oxide. So this, by adding cement to the pure enamel, so we made some mixed enamel. We also call it chemically reactive enamel because it contains calcium silicate. So this flow chart just shows the enameling process for the enamel coating. First, the enamel flakes or grounded into powders, and these powders were mixed with water and other electrolytes to make some enamel slurry. So then some steel bars were dipped into the enamel slurry, then moved into a furnace, firing at 810 degrees C for 10 minutes. After that, take out of furnace and cool it down. So we get some enamel coated steel bar. Looks like this. So how about the structures of this coating? Because we know the corrosion resistance is depending on the microstructures. So this is the SEM images for 3 enamel coatings: pure enamel, mixed enamel, and double enamel. So for the pure enamel coating, we can see the surface is smooth, but there's some air bubbles. And so this is a cross-section view. We can see this actually the air bubbles are released during the enameling during the firing process because there's some oxides. This oxide will react with carbon inside the steel to produce some carbon dioxide. And the thickness is around 300 micrometer. As for the mixed enamel coating, we can see the surface is much rougher. And for the cross-sectional view, we can see there's some connected channels, right? This is connected channel, so it looks like it's not good for corrosion. And the thickness is around 250 micrometer. As for the double enamel coating, the surface is also rough, and also 2 obvious layers can be observed from the cross-sectional view. So the inner is pure enamel, outside is mixed enamel. However, this pure enamel, the air bubble, the size is much bigger than this one. And for the outside mixed enamel, so we did not see any interconnected channels. And the thickness is around 300 micrometer. So how about that corrosion performance? And we prepare some samples and we do some corrosion tests. So this is a steel bar, and this we also prepared some uncoated steel bars. This is uncoated, and this is pure enamel coated, mixed enamel coated, and the double enamel coated steel bars. And we put them in a mortar cylinder. So this is the size of mortar cylinder. The diameter is around 1.5 inch. The height, I think, is around 4.5 inch. And we put this mortar cylinder in 3.5 weight sodium chloride solution and tested them for a period of 173 days. The technique we use include open circuit potential, linear polarization resistance, and electrochemical impedance spectroscopy. So this is a result impedance for the uncoated, pure enamel coated, mixed enamel, and double enamel coated steel bars as a function of time. So it's really difficult to compare the resistance from these diagrams. And actually we proposed the 2 electrical circuit to fit the impedance result. So this model is used to fit the mortar specimens with uncoated and mixed enamel coated steel bars. And for this one is for pure enamel, double enamel coated steel bars. Here we can see the different pairs of CP and resistor. So for these 2, CP and CRC corresponding to the coating properties. And for these 2, is associated with the corrosion properties is the double layer. It's actually the electrocyte and the steel interface. And also as a pair related with the passive film resistance. So this table just shows some parameters extracted from the impedance results for uncoated and mixed and uncoated steel rebar. Actually, we're interested in the coating resistance. For uncoated steel bar, the coating resistance actually is mortar resistance. For the mixed enamel coated steel bar, we can see this coating resistance is much higher than the mortar resistance because it's a combination of mortar and the mixed enamel coating. So how about the corrosion resistance? So this is a comparison of charge transfer resistance. Charge transfer resistance actually is proportional to the corrosion resistance. So we can also call it corrosion resistance. So we can see here So enamel coated steel bar, the charge transfer resistance is much higher than uncoated steel bar, which means this makes the enamel coating has a high corrosion resistance. So how about pure enamel coating and double enamel coating? So we can see this coating resistance is also much higher than the uncoated steel bar. And the corrosion resistance for the pure enamel coatings is much higher. It's around 2 or 3 megohm. And for the mixed and double enamel coatings, we did not get exactly the values of this charge transfer resistance, but it's greater than 10 megohm. So looks like this pure enamel and double enamel also have very high corrosion resistance. So how about the surface? This is surface condition after the test. So we can see for uncoated steel bar and mixed enamel coated steel bar, there's some corrosion product on the surface. However, for pure enamel and double enamel coating, we did not see any corrosion products. So looks like pure enamel and double enamel are good. So we also do some tests to test the bond strength. So this is a per out test, and this is a specimen. It's a mortar cylinder. It's dimensions. The mortar we made this with a water similar ratio 0.5 and a sand to similar ratio 2.801. So this is the machine for per out tests. So how about the results? So here is comparison of bond strengths for uncoated and pure enamel and mixed enamel coated steel bars. So for this bond test, we did not test the bond strengths of double enamel coating. So we can see both enamel coating increase the bond strength of steel bar, and the mixed enamel coating is much higher than pure enamel coating. If you remember in previous slides, we see the surface image, the SEM image of mixed enamel coating. The surface is much rough, so that's because it's some mechanical interlocking and also a chemical bonding. So that's another one is enamel coating modified with sand particle. So actually this is some SEM images, some microstructure of sand particle modified enamel coating. So this is surface view. So it's much rough. And here this cross section, we can see here, this is sand particle and sand particle. And also there's some air bubbles inside the coating layer. And if we take a close look at the surface images, this is sand particle. If you see, there are some cracks, right? For this sand particle, there's some cracks. For this one, there's no crack. I think the reason for this cracking is because this sand particle has different coefficient of thermal expansion as a enamel coating. So in the cooling process, so some crack happens. So how about the corrosion resistance? And we tested the corrosion resistance for sand particle modified enamel coating with different percentages from 5% to 17%. So this is samples we prepared. And the solution is also 3.5 weight sodium chloride solution. And the test lasted for 1 month. So this is a comparison of corrosion resistance after 1 month. So as a function of the weight of sand particles, we can see here with the increase of percent of sand particle, the corrosion resistance decreased. Why? Because more sand particle, more cracks, right? So the corrosion resistance reduced. So this is surface conditions after the corrosion test. We can see some corrosion products on surface around some sand particles. Actually, this is probably there's some micro cracks around this sand particle. So we can see, so I think the reason is because the sand we use is not uniform, probably, but for this one, like for this sand, this is good. There's no crack, no corrosion. But for this one, it's not good. So I think for future, in future, we should select some sands with uniform properties. So question 3 is how to monitor steel corrosion in concrete. Actually, this is research work I was working when I was a postdoctor. So actually, a lot of current technology have been developed, including the electrochemical-based method and non-electrochemical-based method. And for the electrochemical-based method, it consists of half-cell potential, linear polarization resistance, ERS. So this table is from ASTM C876. It's a standard. It's a open signal potential with respect to the probability of corrosion. For example, if the open OCP is much negative than 350 millivoltage with respect to copper and copper sulfides, so the probability of corrosion is over 90%. So this is concrete resistivity, and the different values corresponding to different likelihood of corrosion. And this is corrosion rate and polarizing resistance. And there are also some non-electrochemical based methods like ground penetrating radar, acoustic emission, also some piezoelectric transducers, and optical fiber sensors. So what is an optical fiber? An optical fiber is actually a fiber made of glass or plastic. It has size like human hair. However, it can be used as a waveguide to transmit light between the two ends of it. So it has many benefits. It's small, so it's lightweight. It's made of glass or plastic, so it's immune to electromagnetic interference. So it's widely used, like in areas of communication, infrastructure, aerospace, and oil and gas industrial, and the power transmission, and so on. So what's the basic structure of an optical fiber? So this is a optical fiber cable. It consists of many small cables. If you take a look at this one, so this is one small cable, and also it consists of many pieces, single piece of optical fiber. So the optical fiber actually has 4 layers. The outer layer is the outer jacket, and the second layer is the coating or buffering layer. So these 2 outer layers are used to protect these 2 inner layers from damage. And the third layer is a cladding, we call it cladding. And the last one, the inner layer, we call it a core. Actually, both of cladding and the core are made of glass, so it's very brittle. And the diameter, like for a single mode fiber 28, the diameter of the core is around 8 micrometer. The cladding is 125 micrometer. As for the coating, is 250 micrometer. So this is a basic structure of an optical fiber. So this bare fiber cannot be used as a sensor purpose. So for sensors, some grating need to be written inside the optical fiber. So what is a grating? So an optical fiber grating is a periodic modulation of the refractive index of a fiber by ion implantation or laser inscription. So this is like a optical fiber, this is cladding, and this is core. So here we call it grating. The length between the grating, we call it grating period. So these 2 just show some technology used to fabricate the gratings. So the left one is point-to-point writing by using carbon dioxide laser. So this laser is controlled by the computer. And here we have a fiber fixed at translation stage. And this translation stage moves at a constant speed. So this laser shoots onto the fiber and to modify the refractive index of this fiber. So it looks like this one. Another one is face mask writing. Face mask writing means we need to use a face mask. The face mask actually is a photoresistant materials. So when a ultraviolet laser shoots onto the face mask, it has some pattern that looks like this one. So this is some laser beams will interfere, right, after passing this face mask. So to produce some periodic pattern. So this is we call it a phase masquerade technique. And for corrosion sensors, so far, only 2 types of optical fiber are used for corrosion sensor purpose. The first is FBG sensor. FBG sensor, so this is a sensing principle for FBG sensor. So this is a FBG sensor grating period is usually in the order of nanometers. It's like 100 nanometers. So it's very, very small. So when a light traveling through this, this is optical fiber. Some lights will be reflected back. So this is a reflected spectrum. And here, this peak, this wavelength corresponding to the peak, we call it resonant wavelength. So this resonant wavelength is a function of the refractive index of the curve, as well as the grating period, the distance. So if this grating of this optical fiber, we apply a tensile force, right? It become longer. So the grating changed. So this change of grating would result in a shift of this resonant wavelength to this one. So by monitoring or by recording the change of the resonant wavelength, so we can indirectly monitor some corrosion. This is RPG sensor. RPG means long periods. The periods is usually between 100 micrometer to 1 millimeter, so it's longer than the FBG grating. So here also we have a input light. So this is a wavelength, and this is a output light output. We have a valley. So this the wavelength corresponding to the valley, we call it resonant wavelength. And this resonant wavelength is a function of the refractive index of the curve, the refractive index of colliding, as well as the environment. So this is a sensing principle of RPG sensor. So actually for corrosion purpose, we mentioned in the beginning, corrosion will cause concrete cracking, right? If the concrete cover cracking, so if we put some FBG sensor outside the structure, so it's we can monitor the shift of the resonant wavelengths by and indirectly monitor the corrosion. For the RPG sensor, we need to coat a thin layer of materials on the outside of this grating periods, and this layer should be porous and very, very thin. So these thinners will result to very, very short surface life. Actually, so this is a optical fiber corrosion sensor we proposed. It's a iron carbon coated RPG corrosion sensor. So this is a working principle. So we just coat the iron carbon layer on the surface of grating area. So this iron carbon layer, so this is very similar chemical composition of the as a carbon steel, and as the iron carbon corrodes, so this is some corrosion products. So the refractive index of the environment of the iron carbon layer changes from N0 to N0 prime. So this change will result in a shift of the resonant wavelength, right? So this is before corrosion, and this is after corrosion. We can see there's some shift of resonant wavelength. So by monitoring the change of the shift of the resonant wavelength, so we can indirectly monitor the corrosion of the iron carbon layer. So because optical fiber is made of glass, so it's not conductive. So first we need to coat the silver layer. So this is a SEM image of the silver layer. So it consists of some nano-sized particles. And after that, we electroplate a layer of iron carbon coating. And so this is a microstructure, is porous, and the iron carbon has a size around maybe 20 nanometers. So this is a iron carbon coated fiber. If you remember, I mentioned the diameter of the colliding is 125 micrometers. This one after coating is 165 micrometers. So the coating thickness of the layer is around 20 micrometer. So this is before corrosion. After corrosion, we can see the diameter increased to 400 micrometer. So this is corrosion product. And also we designed some optical electrochemical test setup to test the optical property as well as the corrosion resistance of this iron carbon coating. So here, this is iron carbon coated RPFG sensor. So this is here, this connected with a BBS. BBS actually is a laser source. And this, the other end will connect with OSA. OSA is optical spectral analyzer. It's used to record the transmission spectrum. And also, we measure corrosion resistance of this iron carbon coating. It's a typical 3 electrode system, and this is actually a gamma ray system. And this is iron carbon as a working electrode, and this is SC as a reference electrode, and this platinum as a count electrode. So this photo is just the testing in the lab. So this is ERS, and this is laser, and this is OSA. The solution actually is 3.5 weight sodium chloride solution. So let's take a look at the results. So this is a evolution of transmission spectrum as a function of time from the beginning to 30 hours. So and we extract the resonant wavelengths. So here it can be seen 3 stages. So in the first 9 hours, there's a rapid decrease, and after that a slow increase, and some stage 3 is stabilization. So how about the corrosion resistance? So this is a EIS result for the iron carbon coating layer over time. And also we use this electrical circuit to fit this impedance results. And so we extracted some parameters. So this charge transfer resistance, if you remember, so this is the only parameter is closely related to the corrosion resistance. So now this is figure just show the correlation between the resonance wavelength change and the corrosion loss of the iron carbon coating. So this eta actually is a parameter we introduced based on the charge transfer resistance from the EIS test. So we can see here, when the corrosion loss is less than 17%, there's a linear relationship between the change of the resonant wavelength and the corrosion mass. So we can use it as a corrosion sensor. And also we investigate its sensitivity, its range, and also service life with different coating thickness. For example, we can see like if the inner silver layer is 0.8 micrometer, and the sensitivity decreased with the increase of the outside iron carbon coating. And also, this similar to the range of the resonant wavelengths and the corrosion-induced mass loss also decreased as the increase of the thickness of the iron carbon. And however, for the surface life, with an increase of iron carbon thickness, the surface life increased. But for the silver coating with 1.2 micrometer, the sensitivity is not changed significantly as a function of the thickness of iron carbon coating. Okay. So this is a parameter, a summarize of the sensitivity range and surface life for this iron carbon coated RPG corrosion sensor. So also we do some tests to see the application in concrete. So this is a mortar specimens. So this is steel bar, and we attach this fiber corrosion sensor onto the surface of steel bar. So this cross-sectional view, and this is concrete. This is mortar, and this is steel bar, and this is optical fiber corrosion sensor. And so we put this specimens in 3.5 weight sodium chloride solution. And so this is the result. And the horizontal axis is the change of the resonant wavelength of this optical fiber. And this one is the mass loss of the steel bar. So we can see here, this actually this iron carbon coated corrosion system can only be used to monitor steel bar like for 14 days. So it's very short. Why? That's because if you remember, the thickness of the iron carbon is 20 micrometers. It's very, very thin. So it cannot last for long periods. Okay, probably. So last question is how to assess the structure performance of the corrosion. So actually, maybe okay. So actually, there are two methods so far. One is deterministic approach. The other is probabilistic method. For example, if we have a reinforced concrete beam simply supported, and the steel bar is 319 steel bars subject to corrosion. Like for the deterministic approach, we just we test, we apply a load, and we monitor the loading and also the middle span deflection. So this is a curve. For example, this is a shear strength as a function of the corrosion loss. We can see here. So this is for the reinforced concrete beam with a corroded steel bar is 27%. We can see the loads decrease, also the deflection decrease. And there's another one is probabilistic method. Is also we use some probability density function, and so we use a reliability index to evaluate, to quantify the effect of the corrosion. So this just shows this like a reinforced concrete beam, and when the steel bar subject to corrosion, and this is a failure of probability for this beam. So we can see it increase as a service life. As this reliability index, it decrease as a function of the service life, like 50 years. Why? Actually probabilistic method is much better than deterministic approach. Why? Because corrosion is a random process. So it's affected by some environmental factors like moisture, temperature, and chloride distribution, and the corrosion rate is time dependent and is spatially distributed. So it's not uniform, it's a random process. And also the concrete cover, we know concrete is composite materials. That has some paste or voids, right? So, and both of them contribute to the randomness of this corrosion. So actually, this is I'll just give you some results due to time limitation. So I just show some results I got recently. So this is we propose probabilistic modeling of the corrosion-induced crack width in the concrete. So actually, this is normal distributed function. So this function is to model the crack width as a function of the corrosion-induced mass of the steel bars, and the curve thickness is 1 inch. So this is okay. Acknowledgements. So my research is supported by U.S. National Science Foundation and also by Missouri Department of Transportation. So I think that's all. Thank you for your attention. If you have any questions, we can discuss now. Thank you. Any questions?
Hi, you're unmuted, so you can ask.
Hi, Professor Tang. Very outstanding presentation. So one question is that what are the limitations of the enamel coating for practical implementation? Like, is there any cost barrier or construction barrier?
Yeah, it's a good question. As for the cost, actually, compared with epoxy coating, and the cost is almost the same. So the cost is not a problem, because if you know the enamel coating, the primary chemical is like silicate dioxide, so it's everywhere. And also as for the barrier, like practical application, I think the only is brittleness. Enamel coating is very brittle. So like for some construction, on some construction site, it's easy to damage. So it's not, it cannot be used for some structures. However, it can be used for some precast concrete structures. So we just coat steel bars and in the factory and coat after coating we for concrete. So we made this precast structure element and we take them to construction site. So this is, I think this is the barrier for practical application. So it's very brittle.
Is there any sort of life cycle cost analysis or life cycle assessment done on this technology?
I'm sorry, could you say again?
Was there any sort of life cycle cost analysis or life cycle assessment of environmental implications done?
No, not yet. So we did not to go too far. So we just focus on the material, the corrosion resistance and the microstructure. So we did not analyze the life cycle of this enamel coated steel bar. Yeah.
So in that case, what about service life models, like using your bar versus a conventional epoxy bar or black bar? How would that differ in a typical marine environment, for instance?
Yeah, actually we did some tests, the corrosion test, like we made some mortar cylinders and reinforced with epoxy coated steel bar and enamel coated steel bar, and we found that actually enamel coating is the corrosion resistance is not good, and there are also some painting corrosion. Is similar to the epoxy coating, and the corrosion rates. As for the corrosion rates of the enamel coated steel bar and epoxy coated steel bar, I think probably the same order.
Sorry, I'm confused. Then in that case, why do we propose? I mean, why do we want to pursue this technology then, if it's not significantly better?
Oh, yeah, that's a good question. The reason we propose this enamel coating is because it has chemical bonding with a substrate steel. It has chemical bonding, and unlike epoxy coating, epoxy coating, the bonds between the epoxy and the steel is physical. It's not, but for enamel is chemical, because it's, if you know, the coating process is very high temperature, so the enamel reacts with substrate steel to provide some chemical bond. And the other.
Yeah, sorry. So you're implying that maybe in the real service environment, when there's maybe some sort of traffic loading or seismic activity, this technology will actually win.
Yes. That's because the bond is much higher than epoxy coated steel bar. Yeah.
Okay, we have a question from Galen Johnson. Do you want to go ahead, Galen? Okay, if not, he doesn't have a microphone. Okay, so his question, he posted his question, I need to. Any comment on corrosion protection of welded or threaded connections of reinforcing?
Sorry, I'm comment for what? Oh.
On corrosion protection of welded or threaded connections of reinforcing. You can also read it in your question pane.
Let me see. Actually, it's as for the welding or connection, I think this enamel coating is not. But it's a good question. Actually, I did not look into that. So it's It's a good question. So maybe like in future, I'll try to look into that.
Okay.
Mm-hmm.
Any other questions? You can raise your hand or post a question. Okay. All right, Jiangmin, you can unmute yourself. So, yeah, Jiangmin, you self-muted, so you can unmute yourself. All right, there we go.
All right, here we go. So for the second technology, you were talking about fiber optics. My original impression was always like fiber optics are very expensive to implement and not durable in the long run. Is that the case right now, or?
Yeah, actually, the optical fiber is not expensive, and it's cheap, and the only is because the surface life of this optical fiber synthesis is not very long. It's because the coating layer, the iron carbon coating layer is only 20 micrometer, so it cannot be used for long-term corrosion monitoring.
Okay. And also the glass fiber, wouldn't you be worried about potential alkali silica reaction between the glass fiber and the highly alkaline one?
Yeah, that's a good question, because actually this is, and also we come up with this question like several years ago, but we did not test this durability like in an alkali solution. Probably it's good. So I think it's probably it's not durable like in alkaline environment, because it's glass, right? Reacts in alkaline environment. So, but we did not do some tests. Yeah.
Yeah. So maybe in the future there's some way to minimize this.
Yes. That's a good suggestion. Thank you.
Now I know some of my students are, having time conflict. So if we have other follow-up questions, I'll email you.
Okay, no problem.
All right. Well, if no one else has questions, I'd like to thank Dr. Tang for presenting today, and this will be posted on the website sometime tomorrow. And at that note, I'm going to end the webinar. Thank you all for coming.